Welcome everyone. My name is Puneet Jubahanaya from SIGCOM Research Group, SNT, University of Luxembourg. And today I'm going to talk about clustering-based adaptive beam footprint design for 5G urban macro cell environment. Before I start, I would like to provide an outline of today's presentation. Firstly, we're going to start with introduction, and then we're going to talk about the system model, and then we're going to define the problem statement, and we will propose the proposed solution, and then we'll have some results, and finally, we're going to conclude. To begin with, introduction. The advancements in beam steerable antennas and pattern reconfigurable antennas have made it possible to steer the signal power in the direction of interest. Consequently, they can help in mitigating the co-channel interference, improving SINR at the receiver side, and increasing the throughput at network nodes. On the other hand, dense urban EMBB environment have highly mobile users. Hence, they hand over from beam to beam very quickly, thus creating scenarios of overloading or underusing of the beams. Therefore, we propose a clustering-based adaptive beam footprint design that minimizes the overloading or underusing of the beams using beamforming. We're going to now talk about the system model. The system model is a 5G urban macro cell environment. Here, each eNode B has 3 cells, which is served by using 3 beams. The environment is based on the guidelines defined in report ITU RM IMT 2020 evaluation. This is an evaluation report for 5G radio technologies. And then the environment is, in this example, is based on urban environment with high user density and traffic loads focusing on pedestrian and vehicular users. We're going to define the problem statement now. Problem statement. The antenna bearing orientation angle, which is popularly known as the azimuth angle, in the benchmark has 3 fixed beams whose center directions of the main antenna lobe have 120 degrees separation from each other. This can be seen in the first figure where the 3 beams are 120 degrees separated. And also the elevation angle or the tilt angle in the benchmark is again fixed. In the case, for example, we can consider it to be 15 degrees. Hence, this will make the beam positions and consequently the beam footprints as a fixed design. However, the users in the 5G macro cell environment are mobile and they will move dynamically and they'll move from one beam to the another. Hence, there is a scope to develop adaptive beam footprints. The proposed solution. First, we evaluate the optimal number of beams and then we evaluate the perfect beam positions for these number of beams. First, evaluation of the optimal number of beams. Choosing the number of beams defined as K is not standardized and left for operators' implementation preference. However, choosing fewer number of beams creates beam overload and does not fully exploit spatial diversity. Consequently, choosing too many beams will result in higher interbeam interference due to the overlap of the main lobe with adjacent beam side lobes. The best value for the number of beams is indistinct, and the possible values depend on the shape and the scale of the user distribution. Therefore, in this work, we use cluster analysis to define the optimal number of beams as K. Generally, increasing the value of K will reduce the number of error in the user clustering. Hence, zero error could be achieved when each user is considered as a cluster. However, having a beam for every user is not an optimal solution. Such solutions fail to exploit the spatial diversity benefits and cause interbeam interference. Hence, the optimal decision of K is a right balance between the highest compression of the users using single cluster and the highest efficiency by assigning each user to its own cluster. Accordingly, to evaluate the optimal number of beams, we propose the CH criteria to select the best value of K for a given user distribution. The optimization problem in the equation 1a is called the CH criteria. Any value of K that maximizes the CH criteria is an optimal number of beams, where M is the total number of users, N of K is the number of users in a cluster K, M of K is the centroid of the cluster K, M is the mean geographical location of all the users. Once we know the optimal number of beams, we evaluate the beam positions. First, we group the users into clusters and serve them under one beam. In other words, we partition the M users into K number of clusters denoted by G1 to GK with centers denoted by CG1 to CGK, and each cluster will be later converted to a beam. The optimal number of beams could be found out by an optimization problem we define here. The objective function is a weighted distance formulation. We have a first constraint that is shown in 2b, which ensures that all the users are under the coverage region. 2c assures that any user will be served by only one beam. 2d ensures that the beams have at least one user and we avoid planning beams with zero demand. And lastly, the 2e is a two-element vector in 2D Euclidean space representing the weighted cluster centroid of a cluster K. The optimization problem, which we have defined in the previous step, is solved using Lloyd's iteration partition clustering algorithm. As the first step, we choose the initial cluster centers, that is, we call as the cluster seeds, using k-means plus algorithm. And we run it in a while loop, that is until the cluster assignments do not change or the maximum number of iterations is reached. First, we compute the distance matrix, which is denoted by R, which is of the size K cross M. And this matrix denotes the distance between each of these centers and all of the users. And to do this, we use a weighted Euclidean distance formula, which is given by the equation number 3. And as step 3, we assign all these users into K clusters based on the minimum distance between the users and the cluster centers. And as the fourth step, we compute the new cluster centers using equation number 4. At the end of the Lloyd's iterative partition clustering algorithm, we will have clusters G1 to GK with centers CG1 to CGK, which should be converted to beams, for which we have to compute azimuth and elevation angle, which can be done by simple geometry. In the next stage, we're going to talk about the simulation of the proposed solution. The figure on the left is a benchmark beam footprint planning design where we consider 8 beams which are equidistant from each other. Whereas on the figure of the right is a proposed beam footprint where the 8 beams are being solved using adaptive clustering based algorithm. Some results. The objective of this work is to distribute the total demand across all the beams as evenly as possible. And this will make sure that beams are not overloaded or underused. Accordingly, on the figure to the right, you can see that the fixed beam footprint design has the worst demand distribution, whereas the adaptive design using only k-means has shown some improvements. But while we consider demand into consideration, the proposed adaptive beam footprint design performs the best. The result number 2 is the mean absolute error. Mean absolute error is a measure of errors between ideal demand distribution and the observed demand distribution, and it is expressed using this equation. The CDF plots explains us that the error between the ideal demand distribution and the observed demand distribution is less in the proposed scheme than compared to the benchmark. The Jane's Fairness Index is a well-known fairness metric, which is in this context measures how evenly the demand is distributed across all the beams, and it is defined using this equation. The value of Jane's Fairness Index will vary from 1 by k to the k, where more the value of the Jane's Fairness Index, that means the demand is better distributed. And we run this experiment for 1000 iterations, and you can see that the proposed adaptive beam footprint design performs better than the fixed beam footprint design, and also it performs better than the adaptive design that uses only k-means. That comes to the conclusion part of this presentation. This paper proposes a novel adaptive beam footprint design where instead of steering the beams to fixed locations, the macro base stations steer the beams adaptively to the positions positioned by the adaptive beam footprint design. The proposed ABF design is highly successful in distributing the traffic demand evenly among all the beams, and hence avoiding beam overloading or underuse of the beam. A possible extension of this work would be to design beamforming vectors to generate directional beams for the proposed adaptive beam footprint, and furthermore, verify the user satisfaction by computing the offered capacity to the users. Thank you for your attention.